the next presentation. This is by Adrian from Barcelona Supercomputing Center. And the title of the presentation is Static Analysis to Enhance Programmability and Performance in OmpSs-2. Okay, Adrian, get started.
Hello everyone, and thank you for coming. I am Adrián Munera from Barcelona Supercomputing Center, and today I'm going to present my work, Static Analysis to Enhance Programmability and Performance in OmpSs-2. To start with a bit of motivation, as you probably know, nowadays the field of computing is dominated by hardware heterogeneity in both high performance and embedded system domains. Our applications run in very different multi-core machines with different architectures and different accelerators. This raises the need of a parallel programming model in order to exploit these machines and obtain productivity. The key aspects of the models are that they provide programmability, hiding the complexity behind writing parallel programs. They provide portability, so applications can run on heterogeneous systems, and also provides performance and scalability, exploiting the hardware resources of parallel machines. There are several parallel programming models that achieve this, for example, NVIDIA CUDA, OpenCL, OpenMP, OmpSs, or OpenSs-2. Some of the main advantages of the parallel programming models are that they provide a high-level API that helps the programmability, and they are also typically based on compile time directives, so they allow incremental parallelization, maintaining the portability. Also, some models are task-based, so they provide fine-grained parallelism for unstructured applications. This work focuses on OmpSs. OmpSs is a task-based programming model which main goal is fast prototyping tasking features to include them in OpenMP. Since the beginning of OmpSs, many of the features such as the task dependencies, task loops, task reduction were first implemented in OmpSs and later included in OpenMP with the new specifications. Also, the new version of OmpSs that is called OmpSs-2 is introducing new features like the with dependencies that I will explain later in this presentation, and are expected to be included in OpenMP in the upcoming specifications. This is the outline I will follow during the presentation. First, a quick introduction to OmpSs-2, and then an explanation on the proposed compiler algorithms, autoscope and auto-release, plus an evaluation. Finally, I will end the presentation with some implementation details and discussion. OmpSs-2 works as a thread pool-based model. So at the start of the application, a pool of threads is spawned, but only the main thread continues the execution. It's very similar to an implicit OMP parallel and OMP single in OpenMP. And at the end of the execution, all the threads are joined like an OMP barrier. So when a thread encounters a task construct, it creates a task that can be executed by any of the spawned threads, exactly like OpenMP does. Each task has the typical data sign attributes to define the visibility of the variables. And tasks are synchronized using task dependencies and synchronization constructs as the task weights. Thanks to this synchronization, it is possible to build a task dependency graph that represents the parallel execution of the program. Regarding the task dependencies, apart from the typical in-out and in-out from OpenMP, OmpSs-2 defines new clauses. For example, concurrent. Concurrent works as an in-out dependency, but allows the concurrent execution with tasks with a concurrent dependency on the same object. In the example below, the task T3 has the variable B as concurrent, so it is an in-out dependency, but all T3 tasks can run in parallel. Also, the commutative clause also works as an in-out, but allows reordering the task with the same commutative dependency. However, commutative tasks cannot run in parallel. In the example, task T2 has the variable A as commutative, So it is an in-out dependency, but the T2 task can be executed in any order. Finally, the task waits affects dependencies and work like an empty task. So you can wait to a specific task to finish. When talking about nesting, OmpSs-2 defines a new type of dependency that is called a weak dependency. This means that the object is only accessed by a children task. Thanks to the weak dependencies, nested tasks have its own dependence domain, so the parent task can start its execution and avoid fake dependencies with other tasks. In the example on the right, task T1 declares the X variable as a weak dependency because it is only used inside the children task T2. And as a consequence, the X variable is released only after T2 finishes, and also task T3 can start before T1 finishes, avoiding this fake dependency. Also, OmpSs-2 allows to release dependencies manually using the release directive. So if the user knows that a memory section is not used anymore inside the task, it is possible to release it. And other tasks that had a dependent on it can start before waiting to the task to finish. In the example, task T1 releases chunks of the data array since they are no longer actors, and the corresponding task T2 that has an input on that chunk of the array can start the execution without waiting the full T1 task to finish. Taking into account the peculiarities of OmpSs-2, we developed an auto-scoping algorithm for the data setting variables and an auto-release algorithm for releasing task dependencies. So the main goal of the auto-scoping is to automatically detect the correct data setting attributes for each variable of a task. This improves programmability because it is easier to the user and improves correctness, avoiding possible human errors. Previous works tackle the automatic scope of variables. Some of them define a set of rules for parallel regions that maintains the performance. Others center in autoscoping OpenMP task with a high success percentage. And also others add task synchronization, improving the scoping but harming the performance of the applications. The workflow of the autoscope starts with a source code of an OmpSs program that contains a task in an intermediate representation that is understood by the compiler. And then the autoscoping analysis is applied, which consists in obtaining the synchronization points of the task, obtain the concurrent code to the task, and finally determine the final data setting. As a result, the code is modified, adding the corresponding data setting to be finally compiled into the object file. To illustrate the algorithm, I'm going to use this example on the left. It consists in one big task, T1, that contains two nested tasks, T2 and T3, plus a synchronization task wait. On the right, we have the control flow graph that represents this code. First, we assign 1 to the X variable, and then we create the task T1. Inside T1, task T2 and T3 are created, and finally we have the task wait. The objective will be to autoscope the variables inside T3. That is the task that is marked in color in this graph. The first step is to obtain the pre and post synchronization points of T3. Since T3 is a child task, it is synchronized with his parent task, T1. This is the first pre-synchronization point. Also, as the variable y is an output for task T2 and an input of T3, it is considered another synchronization point. Finally, after the creation of T3, it is synchronized in the task wait. This is a post-synchronization point because no code after it can be concurrent with the task T3. Once we know which are the synchronization points of T3, only the code between the pre and the post synchronization can be concurrent with T3. In this case, the only concurrent node is the one that represents the Y++. To determine the correct data setting for each variable, we must check the use of those variables, both inside T3 and in the concurrent nodes with T3. As can be seen, the X variable is read inside T3 and not used in the concurrent node. For the Y variable, it is read and written in both places. With this information, we can apply the rules that are described in the cited paper to decide the data setting of the variables. For the X variable, it should be a first private, and for the Y variable, since there is a race condition, the algorithm decides that the best scope is first private in order to avoid the race. So we have tested this algorithm using 12 benchmark that uses tasks. In the table on the left, they are divided in benchmark with nested tasks, iterative and recursive methods. And in the table on the right, we have how the variables are scoped in shared, private, first private, or undefined in case the algorithm fails. Finally, on the column on the right, it is shown the success rate for each benchmark. All the benchmarks obtain a 100% accuracy except of the floor plan benchmark because it uses variables in system calls and functions that are not defined in the reachable code, so they can be analyzed by the algorithm. Now I will present how the auto-release algorithm works. As before, the input is the source code in an intermediate representation understood by the compiler, and then the auto-release algorithm is applied. We consist in computing the task variables liveness, introduce the releases, and finally an optional step that simplifies the releases. As a result, the code is modified, adding the releases, and the code is compiled into the final object file. For explaining how the auto-release works, I'm going to use the example on the left that consists in a data array divided in chunks. And the code iterates over the elements inside each chunk of the data array. On the right, we have the control flow graph that represents the code. And basically, there are two nested for loops, the first to iterate over the chunks and the later to iterate inside the chunks. So the first step is to compute the liveness of the variables at each point. In the first for loop, the variable I and also the entire data array are alive. Inside the second for loop, in the first iteration, the variables I, j, and the data array except the first chunk are alive. And finally, after processing the chunk, the variables I and j are still alive, but that chunk is not alive anymore. So this means that the element processed inside the second for loop becomes dead. So it is declared as a dead out. The algorithm can now introduce the release of the element after the processing, since we know that it is not alive anymore. Finally, as an optional step that is still work in progress in our implementation, we can move the release outside the second for loop. Doing this, we release the entire chunk and not each element one by one. Since there are less release calls at runtime, we reduce the runtime overhead. For evaluating the impact on performance, we use the same example as before, but now we have a second task that takes as the chunks of the array as an input. We process the data array in two different configurations. We have first a super fast process that, as the name says, is very fast, but the size of the data array is large. And then we have a fast process that has a normal speed, but the size of the array is small. So for each type of process, we evaluate the execution time with no releases, a release within loop, and a release outside the loop. As can be seen in the table, in both cases, we obtain benefit for introducing the release. And especially in the case of the super fast process, if we move the release outside the loop, we obtain even more benefit since we reduce a lot number of calls and the runtime overhead. Now I will detail a bit on how the analyses are implemented. We have implemented the algorithm in LVM using a Clang frontend that transforms the OmpSs pragmas into intrinsic instructions. We compile the source code with the mend-to-reg and loop rotate transformations, since they are required to later apply the loop analysis in LLVM. And we also use the LLVM link tool in order to merge all the IR files of the source code. And then we have implemented an OmpSs analysis that is composed by the autoscope and the auto-release algorithms. For the autoscope, we make use of the dominator tree and the alias analysis of LLVM. And for the auto-release, we also use induction variable uses, loop analysis, and scalar evolution, and also our own liveness analysis for the variables. Once the analysis is done, the results are passed to the transformation phase that will remove all the intrinsic calls that were introduced by the frontend, and will introduce the actual calls to the OmpSs runtime. And finally, the binary object is generated. So let's finish the presentation talking a bit about the discussion of this work. And although this work centers in OmpSs-2, the truth is that several features of this analysis could be applied to OpenMP, for example, for the automatic detection of task data settings. And also some of the features of OmpSs-2 are going to be included in OpenMP in the upcoming specification, such as the commutative and the concurrent dependencies. Also, OmpSs-2 forces parent tasks to cover all the dependencies of children tasks, making use of this weak dependency. This could improve safety in OpenMP to be used in critical real-time systems. And finally, the release directive does not exist in OpenMP, but other models have similar features, so the algorithm can be applied for them. As a conclusion, we can say that this work tackles programmability, hiding complexity and helping the users, correctness, avoiding possible human errors that can be difficult to detect, and performance, improving the speed up, releasing the dependencies before the end of the task execution. Some work remain as future work, such as the simplification of the releases for the auto-release algorithm, the automatic detection of dependencies that is called autodeps, and the evaluation of the new detached directive of OpenMP. So that's all. Thank you for your attention, and if you have any question, I will be happy to help. Thanks.
Okay, thank you, Adrian. And questions? Okay, while people are thinking about their questions, so can you talk a little bit about the performance aspect? So clearly I can see the programmability and the correctness. So could you explain a little bit more about how the performance improvements can be seen with this approach?
Yeah. The performance improvement is seen in the auto-release. With this, we are releasing task dependencies before the task finishes, once we know that the memory pointer is not used anymore. So if the user doesn't know that or doesn't care about a variable that is not used anymore inside the task and has a dependency on it, this algorithm can automatically introduce the release of that variable. And as you see in the table, we obtain a good benefit of doing it. And I think that that's the contribution to the performance.
So it's due to the release of the variable.
Yes, exactly.
Okay, good. All right, so there is a question. I think actually there are two questions, so let me start with the first one. Have you examined the performance on different devices? What device is the release most helpful?
Yeah, this test of the auto-release is done in a machine with 8 cores. Of course, when you have more cores, the benefit of the auto-release is worse. But in the normal case, with even with 8 cores, we still see a benefit. And in case you use even less cores because you have a different machine that has less cores, you can obtain even more benefit than the one that is shown here. This is for 8 cores running on this algorithm.
So this is Intel.
Yes.
Okay. All right. So there is another question. Does OmpSs plan to introduce the converse of release to be able to relax the incoming dependencies somehow and acquire the compiler would automatically introduce them as the kind of the opposite of release?
I'm not totally aware of the planning of OmpSs-2 nowadays, but I'm sure that they will introduce something similar for sure, because they are testing many things for the tasking. Some of them are new, like the release that is not yet in OpenMP. And for this case, I think that it will be introduced probably in the next version of OmpSs, probably.
Okay. All right. Any other questions? Okay, I have one more question. One aspect in OpenMP task dependencies that dependencies are given with variables. Sometimes these variables are not to the computation, but are only defined for the purpose of declaring the dependencies. Then your release operation is not valid, right?
Yes, if you're using the dependencies just for communication, this algorithm is not valid. But in any case, I think that's not very common. And if it is, you can just disable this auto release and just use the autoscope algorithm.
Okay. All right. Other questions? Okay, any other questions? Okay, and you said that some of these weak dependencies are planned for the next release of OpenMP. I'm not, I don't keep up on the timeline for that. So do you know when OpenMP 6 or whatever the next version is expected?
Just let me go back to the slide. So this is the timeline for OmpSs and OpenMP.
Okay.
And for the last specification that is on B6, they will introduce the with dependencies that is already in OmpSs. So I don't know what are the rest of the things that they will include, but for sure this new feature will be included.
Okay. All right. Thank you. All right. Any other questions?